Hello and welcome. Today, we're diving into the fascinating world of computational fluid dynamics, or CFD for short. Ever wondered how engineers design sleeker cars, more efficient airplanes, or even analyze blood flow in our bodies? CFD often plays a crucial role. So what exactly is CFD? It's essentially using computers and numerical methods to simulate how fluids, that's liquids and gases, flow, how heat moves through them, and even related processes like chemical reactions. Think of it as a virtual wind tunnel or a digital laboratory for fluid problems. It allows us to study complex situations that might be too expensive, dangerous, or just plain impossible to test physically. How does it work? At its core, CFD solves fundamental equations that describe fluid motion, the famous Navier-Stokes equations, derived from basic physics like conservation of mass, momentum, and energy. These equations are incredibly complex, especially for real-world scenarios, so CFD uses a trick called discretization. It breaks down the fluid space into tiny pieces, creating a grid or mesh. Then, it applies methods like the finite volume method, finite element method, or finite difference method to turn those complex equations into a giant set of algebraic equations that computers can actually solve. The finite volume method is particularly popular for its robustness. Real fluid flows aren't simple. They're often turbulent. Think of the chaotic eddies in smoke rising or water rushing down rapids. Modeling this turbulence accurately is a huge part of CFD. Common approaches range from the efficient Reynolds-averaged Navier-Stokes (RANS) models used widely in industry, to the more detailed large eddy simulation (LES), and finally, the extremely computationally expensive direct numerical simulation (DNS), which captures everything but is mostly used for research. CFD also handles other complexities: flows with multiple phases like air bubbles in water, heat transfer through convection, conduction, and radiation, chemical reactions like combustion in engines, the interaction between fluids and structures like wind on a bridge, and even weird fluids like paint or blood that don't behave like simple water, known as non-Newtonian flows. The applications are incredibly diverse. In aerospace, it's used for designing wings and engines. In the automotive industry, it improves aerodynamics and engine cooling. The energy sector uses it for designing turbines and optimizing power plants. Biomedical engineers simulate blood flow to design better stents or artificial heart valves and analyze airflow in lungs. Chemical engineers design reactors, civil engineers model pollutant spread or wind loads on buildings, and manufacturers optimize casting processes. The list goes on. CFD isn't standing still. Faster computers, especially high-performance computing and GPUs, allow for bigger and more detailed simulations. Researchers are constantly developing better algorithms and turbulence models. Artificial intelligence and machine learning are starting to play a role too, helping speed up calculations and analyze results. We're also seeing more multi-physics simulations, coupling fluid flow with other physics, like structural mechanics or electromagnetics. Plus, user-friendly software and open-source options are making CFD more accessible than ever. In short, computational fluid dynamics is a powerful tool that provides deep insights into the world of fluid flow. It helps engineers and scientists design better products, understand complex natural phenomena, and drive innovation across countless fields. By replacing some physical testing with virtual simulations, it saves time and resources, making it an indispensable part of modern science and engineering. Thanks for tuning in.